Hello friends, good morning. Today we are going to start with another session of complex analysis, that is integration of the type 3. In the last lecture we have seen complex integration of type 2, that is composed of algebraic and trigonometric function together. Okay. Suppose if the function is given in the form 0 to 2 pi f of sin theta cos theta d theta. Suppose the integral may come like this: integral 0 to 2 pi 1 by 1 plus sin theta. It is usually in the form 1 by a plus b cos theta, or in the form integral 0 to 2 pi 1 by a plus b sin theta. Here a and b may be some constants. Okay, that is constant, and the limit is 0 to 2 pi, right? This kind of integral we can easily calculate using complex technique, right? So first of all, we have to do is we will make a substitution. The complex function is z is equal to e raised to I theta, right? Then what is 1 by z? 1 by z is equal to e raised to minus I theta. So if I find e raised to I theta plus e raised to minus I theta divided by 2, this is a familiar formula that will be is equal to z plus 1 by z divided by 2, right? This part is we already know this is expression for cos theta, right? Cos theta is equal to, when I am cross multiplying this, z square plus 1 divided by 2z. And similarly, if I do e raised to I theta minus e raised to minus I theta divided by 2, by subtracting these two, you will get z square minus 1 divided by 2iz. Okay, so this is the expression for sin theta, right? So we will substitute in the expression sin theta as z square minus 1 divided by 2iz, and cos theta as z square plus 1 divided by 2z. Okay, and also from it I can find out this d theta as dz is equal to, if I am differentiating this, I can write this as I e raised to I theta, and again this e raised to I theta is my z. Okay, so this is my z. So d theta is equal to what? Dz by iz. Okay, so you have to by heart this result, and this substitution, this result. Okay, if you know all this result, we can substitute in the expression and we can do easily find out the integral. Okay, see, for example, we can do a problem. Then see, suppose you have an integral. Let me go to the blackboard. See, suppose you want to calculate integral 0 to 2 pi. This is a simple integral that we can calculate using ordinary integration. Okay, what is by ordinary integration? Let me check the answer first, then we can come to, by ordinary integration, this we will do by multiplying conjugate 1 minus sin theta divided by 1 plus sin theta into 1 minus sin theta, right? Integral 0 to 2 pi. So this is equal to, I can write this as 1 minus sin theta divided by 1 plus sin theta into 1 minus sin theta, that is cos square theta. So this is cos square theta d theta. Okay, so this will be equal to 6 square theta minus 6 theta tan theta integral 0 to 2 pi, right? So when I am integrating this 6 square theta on integration, I have the result as tan theta, right? Okay, 6 square theta on integration tan theta, and 6 theta tan theta on integration I have 6 theta. Okay, so this is the final result. So this I can write as 0 to 2 pi. Okay, so tan theta, tan 2 pi and tan 2 pi is 0. So 0 minus, what is sec 2 pi? That is minus 1, right? Minus sec 2 pi. Sec 2 pi is minus 1 or 1? It is 1, right? It is 1. I'm sorry. It is 1. Then when I am substituting this 0 here, tan 0 is 0, minus sec 0 is again 1. So this is minus 1 minus minus, that is plus 1. The answer will be 0. Okay. So this is the result when I am doing with the ordinary integration. Now let me check the answer will be same or not with the complex. So the answer is 0 right now. So let me check using the complex analysis, we can do the same integration. Okay. But the particular question, this question is we can do with the ordinary integration, that is much easier. But if here you have dx plus 2 plus 3 cos theta, like that, it is very complicated. Okay. So we can do this in the complex format. So what I am going to do is this is our question d theta. So I am substituting z is equal to e raised to I theta. Then what are the parameters? That is d theta is equal to dz by iz, and we can sin theta, I can replace by z square minus 2iz. If I am substituting all this in this equation, alright, so I can write the d theta as 0 to 2 pi. This I can write as dz by iz divided by 1 plus sin theta, I can write as z square minus 1 divided by 2iz. On simplification, I can write this as integral 0 to 2 pi dz by iz. On cross multiplication, this we may write this as 2iz plus z square minus 1 divided by 2iz, and this iz I can cancel out. So integral 0 to 2 pi, this 2 I can take to numerator, right? 2 dz divided by this z square plus 2iz minus 1, that I can simply write as z plus I the whole square, right? So from this equation, it is clear that the pole is z is equal to minus I. So if you calculate the residue of this, so this is a double pole, so 1 by 2 minus 1 factorial into limit as z tends to minus I, right? D by dz of z plus I the whole square into 2 divided by z plus I the whole square. Okay. So in this case, there is no variable in the z, in the f of z. So when I am differentiating with respect to z, this constant, okay, the answer will be 0. So we got the same result in the complex integration also, right? So this is the technique we are going to apply here. Now let us go to the main board and we can do one more question based on this. Okay, one difficult kind of question we can do from it. Okay, so the so here this is the question: integral 0 to 2 pi d theta divided by a plus cos theta. So what I am going to do is 0 to 2 pi d theta a plus cos theta. Here I am substituting d theta is equal to dz by iz, cos theta is equal to z square plus 1 divided by 2z. On making the substitution, I can write this as minus 2i. I am going to take out. This is 2az, right? So this is a, and here 2az. So we have some problem here. So I can write this as 2az, right? Cross multiply this 2az plus z square plus 1, and this 2z will go up, that is 2 is there, and here we have new denominator, we have 1i. So I am multiplying numerator and denominator with I. So I square is minus 1, so I can take minus 2i out. Okay. Now this 2z square plus 2az plus 1. This I am going to write by factorization. I can write some z minus alpha into z minus beta, where alpha and beta are the roots of this equation, right? So roots we can find out using quadratic formula. So alpha and beta we can solve by simplifying. Okay. So here alpha and beta are the poles, right? Alpha and beta are the poles. So alpha I can calculate from it, that is minus b plus or minus. So minus 2a plus or minus root b square, that is 4a square minus 4ac, that is 4, right? So I can write this as by 2a, right? 2 into z square coefficient is 1. So here alpha is equal to, the poles are minus a plus, right? Minus a plus root a square minus 1 and beta is equal to minus a minus root a square minus 1. So these are the poles that we can have here. Okay, so we are doing the equation in the limit 0 to 2 pi. So this is our poles alpha and beta. Once I get alpha and beta, this a and b a plus b cos theta format, usually we will have numbers there. So we are doing it generally by considering the constant as a. Okay, so alpha and beta, these are the contour. Now this is inside the contour and this is the outside the contour. Why? See, minus a minus, this negative quantity will increase, right? Okay, so but here minus a plus some quantity. Okay, so the net quantity will decrease. So this part is usually inside the contour and this part is usually outside the contour. Now we are focusing on this. We can calculate the residue using this. Okay, so how can we calculate it? It is a simple pole. So I can find out the residue that is from this formula, right? So this is our function. So I can take minus 2i out, minus 2i. So residue, instead of calculating, we are doing integral limit as. So our residue is at alpha, right? So that is this term is inside the contour, this is outside, so this is not valid. So residue at z tends to alpha, right? Z minus alpha into dz divided by z minus alpha into z minus beta, right? Now this z minus alpha, this z minus alpha will cancel. Now let us substitute, need not dz here, f of z, right? This is f of z, right? Now I can substitute this as minus 2i into, what is this, z minus beta? When I am substituting here, this is 1 by alpha minus beta. What is 1 by alpha minus beta? Minus 2i into, this is alpha and this beta. If I am subtracting this, and this is 2 root a square minus 1. Alpha minus beta is, so I can write alpha minus beta as minus 2i by root 2 root a square minus 1, right? So this is our residue. Once I get the residue, what is the integral? Integral is 2 pi I into sigma residue, So what is residue? 2 pi I into, that we have already calculated, that is this 2 cancel, minus I divided by root a square minus 1, right? So this I and I square minus 1. So 2 pi by root a square minus 1 is the final result. Okay, if somebody know this result, okay, somebody know this result, so if you have any number instead of 1 by 3 plus b cos theta, 3 plus cos theta, okay, then you can take this a as 3. Okay, you can substitute just the value of 3 if you know this result by heart. Okay, so usually in CSIR net examination, some questions may ask like this: 1 by 3 plus cos theta, or 1 by 3 minus sin theta, like that. So if you study the result by heart in the format integral 1 by a plus b cos theta and integral 1 by 0 to 2 pi, okay, 0 to 2 pi, this a plus b sin theta, then you can just substitute. Once you know the result of this, you can just substitute the value of a and b separately in that result. Okay, so that's the method for the examination point of view. Okay, that's I'm not recommending such a way, because we have to do this. Okay, for the examination point of view, you can do that. Okay, now this is the, so our result is 2 pi by root a square minus 1. So this is the result. Okay, so this is all about this session, and here is the last class of this complex analysis, and in the next section we may jump to special functions like Legendre polynomial, Legendre polynomial. Okay, so that all we will discuss in the next class. Okay, thank you.